instance, in any layer. So in the input layer, that was quite simple, right? So you had the whole data set. You could eventually get your all inputs. You just take the average of them. This is going to give you the average input. And then you also compute the standard deviation for every single entry inside your input vector. And then what you're going to do, you're going to just normalize everything, right? So we had it before. Yeah, that was the normalization. So we are going to just subtract every single sample from the mean. We divide it by the standard deviation. This is going to give you what you need when you want to do the training. That was easy with the input. The main reason was that for the input, we do it once, and that's it, right? So you have the whole data set. You do this normalization, and that's over, right? But the issue starts when you want to do it for hidden layers, right? Because when you are doing it on the hidden layers, the features that you get are depending on the weights that compute those hidden features as well, right? And this could be problematic because when you just update, first of all, if you want to just normalize with whole samples inside the data set, you get into this trouble that you need to wait for all the samples to get in the hidden layer so that you have all the features and you do the normalization. This was the first problem. And the second problem is that these features are depending on the weights of that layer. So eventually those mean and standard deviation also depend on the weights, right? And when you want to do backpropagation, it's going to be a problem. So how we can resolve this issue? Well, the basic solution is quite simple. So for the first one is that we are going to just approximate the average on a mini batch, right? So what can we do except we just work with a mini batch because that's the best we could get when we are doing the training. So we are going to focus on a mini batch. This means that instead of averaging over the whole data set here, instead of the complete batch B, you are going to just take one mini batch and average over that. If your mini batch is chosen randomly, then it's fair, okay? That's the first thing. So we're going to approximate over the mini batch, and we just compute the normalization over that. But the issue is that we cannot still run away from the second problem, the problem of mean and variance depending on the weights, right? So now what I'm going to do, I'm going to focus on one single neural network. I'll show you how this dependency is going to happen, right? If you want to do the backpropagation, where does the problem show up, how you can do it. We're going to explain this for one neuron. Once it's clear, you can simply extend it in your mind for a general case. But as I said, the details are given in the slides. If you are interested, you go over slides, you practice at home, and you can do it for a complete neural network if you are trying to just implement it from scratch by your own. So what is the idea here? I am just thinking of one neuron somewhere in the middle of the neural network. So we are in one of the hidden layers. So in that hidden layer, we have a bunch of hidden features in one particular layer, and then the neuron is the neuron of the next layer, right? So this y1 to yn, they're eventually hidden feature of one, say, first hidden layer, right? And this neuron is the neuron in the second layer, right? Second hidden layer. And this guy depends on everybody here, right? So it's going to again multiply with the weights, and then you add them up here. Just to make it simple, I don't consider bias as well, so you don't need to think about W0 anymore. So we have n different features, and they are getting multiplied with their own weights, so it's a linear transform. And what I get at the output is going to be this guy. So I'm now showing it by theta just to differentiate it from y, which is the hidden feature, okay? So this guy is not your input, obviously, right? So you get this, because for input, we don't have any problem, right? So this guy is definitely one of the hidden layers, right? So this means that you had a bunch of inputs. Those inputs pass through your neural network. Now you're somewhere in the middle, right? And you got these features. Now you want to go for the next layer, right? So that is what's going to happen when you just go forward. Now, if you were doing the basic forward, backward. So this means that there is no normalization happening here. Everything is quite simple, right? So for every single sample that you have, say you have omega different samples in your neural network, every sample goes completely forward, right? And when you are going forward, you don't need to wait for anything, right? The first sample goes in, it's going to pass all the way towards the end, and then you backpropagate, right? So you're going to get every single sample. In that particular neuron, you're going to compute the output first, and then you activate it. You pass it for the next layer, right? You don't care about anything. And if you want to do backward propagation, once you got on this particular neuron, the thing that you're going to do, you're going to compute the gradient of the loss with, I mean, you have the gradient of the loss with respect to the output of the neuron. You're going to go backward, right? You multiply once with the derivative of the activation, and then again, you're going to multiply with your linear weights, right? So if you are at that neuron, you don't care about anyone else, right? Because the only thing that depends in that neuron are the guys who are directly connected to it, right? So that is the basic forward-backward, but once we have normalization, now the thing is getting a bit different, right? Now, if you are just sending a mini batch, obviously you need to wait till the mini batch is completely passed up to that layer, right? So if you are in one, say first hidden layer, and you want to go to the next one, you need to wait till all the samples inside the mini batch are there, because you need them in order to do the averaging and normalization, right? So if I have omega different samples inside my mini batch, I obviously need for my first hidden layer, or whatever the hidden layer is, I need all of the samples to get passed, right? So I'm going to see the feature of the first sample, feature of the second sample, so on till the last sample. Know that I have all of those sample features y omega. Then I can just average them over my mini batch. I compute the standard deviation, and then I can do the normalization, right? Everybody's cool, right? This is obvious. You need to wait, right? So it's a kind of extra time you need to wait till it's over, right? I mean, again, obviously this is not going to be a big problem with nowadays computers, because you are not going to compute them really in series, right? You have parallel processors who are, each of them is taking care of one or some samples, right? So you usually get them all together and you can do the normalization. But if you want to think in terms of one processing pipeline, then you need to wait, right? Everybody's cool, right? Okay, so you wait, you compute that. Once you computed that, now you do your normalization, right? So you subtract every single sample from the mean value, and you divide it by the standard deviation. Everybody's cool, right? Now, one thing, everybody's clear, this sigma here, this mu, both of them are vectors, right? And all of these operations that I'm showing to you are happening entry-wise, right? Everybody's cool, right? You see that. So y, if y has two different entries, the mean mu going to have two different entries, sigma is going to have two different entries, right? The first entry of mu is the mean value of the first entry. The second entry is the mean value of the second entry, right? And then you are subtracting every single entry from its corresponding mean, right? Same thing with sigma, right? Sigma, if y is two-dimensional, then sigma is two-dimensional as well. Every single entry is giving you the standard deviation of that entry, right? So I hope that you are getting this idea gradually, that you don't really need to care about what y is, right? What kind of object is. As long as I'm showing something like this, you can think of a scalar, right? And when it's multidimensional, any other form, as long as mu and sigma are the same format, they're going to get the same process, right? In parallel. Sorry? Entries, no. Features, the output of the first hidden layer. So if you have your input, yeah, features that are coming out of, not weights. Weights are on the edges, right? So like you have your MNIS going in, so your input is 784. And then say your first hidden layer is, the width is 100. Then you're going to have 100 output, right? This y then is that vector of 100. Everybody's cool? Okay, so now you have this one. What is the statistics of this one? It's zero mean, right? Somehow, right? Because you have subtracted everybody from its mean value, right? So it's centered at 0, roughly, right? And what about its standard deviation? It's roughly 1, because you normalize everybody with its own standard deviation, right? So it means that this U guy is somehow 0 mean unit variance, right? Everybody's cool, right? Now, one thing that we do in addition is that we do shift and scale. So what is this shift and scale? So you have this U, yeah? You're going to multiply it with with one vector, which is the scaling vector. This means that you don't necessarily keep U unit variance. You might say I want it to be larger in variance or smaller in variance, okay? Why? Because maybe in your application, some variance different from 1 is going to help. Who knows, right? So you are scaling everybody, and you see that this gamma here is again the same size vector, right? So every single entry inside U is getting its own standard deviation, right? Its own variance, right? And then you're going to shift it to point beta, right? So you have your points which are centered at 0. Now you are going to shift them to somewhere, and also you scale them, right? Because who knows, maybe different center point, maybe different variance is going to help you in terms of faster or better learning from data, right? So this is what we're going to do. I'm going to explain more on that because we need to find out what these guys are. But this operation is basically scaling and shifting of your unit variance. So you first took the point, put it at the center. Now you're taking it somewhere that you want. Yes? No, it's not necessarily. It's not random, no. You learn it. You're going to learn it. Okay. It's a weight. Yeah. I'm going to explain it. Yeah, no worries. So once you have done this, then the last thing that you're going to do, so you had your initial y. Those y's came there. You waited for all of them. You just normalize everybody. Now you have 0 mean unit variance. You did this scaling and shift, and then you do the activation, right? So here, what you're doing again is exactly as you used to do before, right? The only thing that is happening here is these guys in between. Like when you are in one layer, before you can go for the next layer, you need to do that process, right? And this whole process is what we call it batch normalization, because we normalize the data by batch, and then we do this scaling and shift, right? Everybody's cool, right? Yes. Yes, because U is at 0, centered at 0 with unit variance, right? But there is no reason for your neural network to learn the best out of this data. Maybe if you put your data if you center it instead of 0 at some other point, say 1, 1, that is better. Who knows, right? So you want to find out where is the best point. And if you just want to have a bit of idea why this happens, think about ReLU function, right? If you have a ReLU function, think your features are two-dimensional. Then the thing that is going to happen, wherever it's distributed, right? So you're going to get anywhere negative cut, right? And then this goes to the next layer, right? So if you put it on the center, then roughly, say, 3/4 of them are going to be cut, right? Whereas if you just shift it up, you're going to get less of them cut, right? If you shift them down, then you're going to get more of them cut, right? Who knows where is the best point, right? So you want to find it out. So you're going to leave it as a general parameter here, okay? Yeah. I'm going to show the diagram. You get it a bit more clear. Questions? Okay, so yeah, so scaling and shifting, basically the idea is that there is no reason for us that center and variance 1 is the best choice. So this is why we do, we shift it to another point. So maybe another point is doing better. And now, one thing that is here, I think you got the idea. I mean, it's not very easy for you to engineer these parameters, gamma and beta, right? So you cannot find out what is the best choice. What is the best idea? We are doing machine learning. Whenever you have a parameter which you don't know what is the best choice, you're going to leave it for the data to decide, right? So you're going to learn that again, right? So you're going to treat gamma and beta to be bunch of learnable parameters, and the only thing you need to do, you need to be able to compute the gradient with respect to them, right? Then you start from some initial choice, and then you gradually update them till they get their own value, right? So gamma and beta are learnable parameters, new weights to your model, and then you just train them alongside with the other weights, okay? No, they change from one layer. So this is just one particular layer. You can change it for. Actually, you can change it for every single neuron in your layer, because we are talking here about one single neuron, right?
But in practice, do you do that or keep the same for the whole?
I guess what you do with PyTorch is that you are just keeping it fixed for one layer. Because if you just make it too much varying, then you're going to make it trouble in the sense that when you are using that for inference, then the weights that are normalizing are much different from your data. So the training data. So your new data is not very well matched because it needs like long time to get converged. I guess you usually keep it fixed for the whole layer, but theoretically you can do it. If your neural network is not too big, you can do it. Okay, so questions? Everybody's cool, right? So the idea, as I said, is like this. So if you have your hidden features, who knows that the best point is center? Who knows that the best variance is to be 1, 1, right? So maybe it's better that you put it at some other point beta, and then you have different variances for every single dimension. If that is the case, then, well, yeah, it's essentially the same thing. When you are doing batch normalization, you are just shifting everybody to that point, right? And you are scaling it proportional to those variances or standard deviations. But the choice of these values are open, right? So you can't just leave the data to decide for those parameters. Okay, everybody's cool? So you got the idea how the process of forward propagation is now happening, right? So the whole batch comes. Batch normalization happens, and then you go for the next layer, right? Yes? Yes, they could be not.
So would the mini batches, like the normalized mini batches, shape different than
Yes, I mean, you could, like, you get this guy, say, and then you just shape it like an oval. You can do it, right, right. Because maybe you want to have more of data in that direction to get caught, but in this direction you don't want to get too much caught. So it's totally depending on your data. Yeah. Questions? Yes?
you normalize the input as well, the data, and then you normalize every layer?
Sorry? You normalize the data, yes, and then that's normalized data, that's over. And then in every layer, you do it again, but you need to do it through training. You cannot do it like once and it's over, right?
So for each layer, the output or feature, you normalize?
Yes, exactly.
And then you go to the next one and normalize?
Yes, yes. And you do it in PyTorch, for example, you have your layer, you call one batch normalization layer. And that batch normalization is doing this stuff for you. Yeah. And the parameters of that layer are essentially that gamma and beta. Okay? Yeah, but you usually do it. Like in simple application, if you don't do it, it's not very crucial. But if your your data is extremely varying in different dimensions, like if it's a totally new data, then this is going to be crucial, especially if your neural network is not very deep and very complex, because then it's not it's not high capacity. And it could be that you start from a random initialization, you converge, you just start from another initialization, you do not converge to a right point, right? And this is eventually, for you in practical sense, this means that this neural network is not reliable. because yeah, it doesn't make sense that sometimes it works, sometimes it doesn't, right? But when you do batch normalization, they're going to work pretty much all the time. At least you see a consistent behavior. Yeah. Yes? Yes, because so the point is that your features are computed by your weights, right? And when your features are computed by your weights, there is no reason that you have same scale input and you get same scale features, right? Right. Yes, of course, definitely, right, right, definitely, yes, yeah. Yeah, if you have a railway activation, for example, some outputs, some features are going to get 0. Some features are like large, right? So those features who are 0, they could potentially be in amplitude very large, but they are simply negative, right? Or if you have a sigmoid function, then it does not really reflect the level of sensitivity that your input has, right? Yeah. Yeah. So, and it's not only about the nonlinear. I mean, if you start with a bunch of weights, right? Who says that? How do you know what are the weights, right? Initially, maybe the weights of one neuron are extremely large. The weights of another neuron are extremely small. The initial choices, right? But then it is going to insist on being large all the time if you don't do the normalization, right? So this simple random initialization is going to give privilege to some neurons and no privilege to some others, right? So you don't want this to happen, right?
So I still need to make my source output more or less localized.
Right, yes. Because what you are thinking, you would say, okay, the same way that I thought about input to the first hidden layer, now I should think the same way for the input to the second hidden layer. Because if the second hidden layer is going to find out which feature is the best one, it should not depend on their scaling, right? It should only depend on the information they are carrying. And the best idea is that I normalize them, right? If I normalize them, then as long as one feature is getting more pronounced in the second layer, this means that that feature is really important. It's not simply because I started with a bunch of large sample values, right?
The way I'm starting my weight with, basically I could have, like my initial values could have like emphasized like a certain
Right,
like
yes, yeah, yes.
So I still don't know.
You still don't know, really. You still don't know, yeah. Yes, but when you are working with your first, say, set of batches, mini batches, right? So your first mini batch is just dealing with totally non-updated weights. The second mini batch is dealing with a bunch of updated weights. The last mini batch is dealing with a very good updated weights, right? So it's not fair that how do you want to pass it to the next layer, right? So actually this kind of behavior, this different distribution of mini batches is going to be more obvious in the hidden layers because after each mini batch you are updating, right? And the weights could change significantly, and that could just take one of the mini batch to another point, right? Make sense? Okay. Questions? After normalization, right? I mean, you can do it before or after, but typically we do it like after normalization. But in practice, you can try both and see which one works better. Okay, so now the key point here that I want to show you is that how does the backpropagation change? Okay, and how does it change? Well, if you think in terms of backpropagation in the basic form, so you have your feature y, right? This is one sample, right? This is a vector of the features for one sample input. And then once you are at this layer, you are going to multiply with a bunch of weights. You activate them, and then you're going to get your output. Then you go on till you end up with your loss, right? So the first sample goes, you just transform, activate till you get to the output, and then you compute the loss, right? Now, if you want to just do backpropagation, everything is quite simple, right? You're going to say, okay, I have the loss. I'm going to get to the last output. Then from that one, before activation, from that non-activated one to the previous layer, and so on. I keep on going till I get to the point that I want, right? But the issue that is happening here is that now you don't have really a connection from one output only to the corresponding loss, right? So your sample loss, or say your whole mini batch loss, is not anymore depending on a single input, right? So it's basically depending on all the inputs in that mini batch, right? So if you are in one particular layer, now here you have omega different samples inside your mini batch, right? And these guys, all of them arrive. After they arrive, you now compute the mean value and standard deviation, right? And those mean value and standard deviation, they depend on all of these samples, right? So there is a lot of connections going on here, right? And then this U1, it's not only depending on its corresponding Y1, right? It depends also on Y2, Y3 till the last Y, right? So this means that the loss you are computing for this particular sample, right? This loss also depends on the value of other features inside your mini batch, right? And if you want to go backward, then you need to also go backward to them as well, right? Because they also appear in the chain rule, right? So what is going to happen? You have this guy, these different Y's. For them, you do the normalization, or what we call it a standardization at this point, because you basically make it zero mean unit variance, right? And once you have done this, the next thing is that you just add that batch normalization operation to it, right? So what you do, you just do this scaling and shifting here, right? And now what we usually mean by batch normalization, we simply mean we get from this Y to the scaled and shifted version, right? This whole thing end to end is usually called batch normalization, okay? So you get from your output into these guys, and after that, of course, everything is as before, right? So anything after this is as before exactly. So if you are thinking in terms of the loss coming, the sample loss coming from this particular top branch, that one only depends on Z1. And Z1 only depends on Y bar 1. But, and this guy only depends on U1. This is okay, but the issue is that U1 depends on Y1, Y2 till Y omega, right? So that is the issue. You see that, right? So that's going to be a problem, and then the whole question is that how we can do the back propagation. Now, I just want to show you for this particular example, how does the chain rule look like? Again, if you don't follow all the details, that's okay, but you need to just get the idea how we are doing the chain rule, right? Yes? This one, right? It's a hidden layer. Y1, Y till Y is the output of one hidden layer. It's not input. Input has no problem, because input, of course, I can just normalize and on my whole data set, right? And that's it. I don't have any problem with that. So Y is eventually one hidden layer in between, like your first hidden layer. And again, when you are at that hidden layer, you again do the normalization. So this is basically the discussion I had before with your friend. So when you are doing that, when this guy comes, right? So you normalize it at the input layer. That's okay. But when it passes through the first layer, it's going to get multiplied with a bunch of ways. It's going to get activated, right? There is no reason that the features you see at the output of your first hidden layer are again distributed the same, right? It's actually, we are doing it on any hidden layer. When you call it batch normalization, you mean that you are doing it on hidden layer. Yes, this is one hidden layer. This is one sample hidden layer. I just think of one randomly chosen hidden layer. And Y1 is the whole input of that hidden layer. So Y1, Y2 is the output for the second sample. So these are different samples. So you don't think of Y1 till Y omega to be all for one layer. Like Y1 is one layer, sample 1, y2 is the same layer sample 2, and so on, right? So these are parallel computations going on, right? No worries. So everything is clear? So these guys are different sample points, right? And these are computing different sample losses. You average them. This is your batch loss, right? Correct? So this is your batch loss, right? Averaged over your mini batch, sample loss of every single output, right? So theta omega is your output for that particular sample omega, right? V omega is the corresponding label, right? You compute the loss, but the key point is that this loss, this theta omega, is not only depending on sample omega, right? It's also depending on the features of the other samples because you have done batch normalization, right? So now what I'm going to do, I'm going to write it down in this form. So when I say R hat omega, I mean sample loss for one single sample, right? But you do know that this guy is also depending on the others as well, and this is the whole complication. Now, how we can do this? Well, if we want to do the backpropagation, the first part is quite simple, right? Getting back from R hat to U, the standardized form of that particular sample, is no problem because everything is just as before, right? So you're going to start from your loss, you're going to get back to your output. From the output, you are going to get to your non-activated output, and from that one, you're going to get into your the normalized one. That is no problem. This is exactly as before. So what I mean that from here, when you have your sample loss, moving backward is no problem here, right? Again, you move backward here, everything is as before, right? There is no problem up to this point. What about getting back from y bar 1 to u1? What is the problem there? Is there any problem, actually? Yes, which is no problem, right? So that one is, again, the same thing as before. It's a new operation. That's OK, but you can simply do it, right? So you can simply get back from those normalized version to the standard versions. So basically what you would say every single normalized version is 1 gamma multiplied with the standard version plus beta. Now if you want to get back from y bar to u, what you're going to do, you're going to write down the chain rule, right? So you would say that, OK, I have the gradient of my sample loss up to y bar, right? Y bar omega. And then if I want to get to u omega, so if I want to just find out what is the gradient of the loss with respect to u omega, then basically I need to write it down as gradient of r hat omega with respect to y bar omega times the gradient of y bar omega with respect to u omega, right? That's the chain rule, right? So here I don't need any extra term, right? I am not going to compute, for example, I could, for example, don't get confused. This is just a dummy thing that I'm doing. I could say that summation I from 1 to omega, so all of the mini batch, instead of computing with respect to u omega, I just write it down ui, right? But the key point here is that every single y bar is depending on its corresponding u, right? There is no connection from the first y bar to u2, right? So that gradient means that this gradient going to be 0 anywhere but the point where I is exactly omega, right? You see that, right? And then I don't basically need this guy anymore. You see it, right? Everybody's clear? So that is going to be the case. Now, you are going to just compute that gradient simply using the chain rule. And yeah, that's going to be your chain rule, right? Oh. That's going to be your chain rule, right? So your gradient with respect to u is going to be simply your gradient with respect to y bar times the gradient of u with respect to y bar, which is going to simply be gamma, right? That's it, right? So That is no problem. You can simply do the backward pass here. At this point, you can also compute the gradient with respect to gamma and beta, right? Because what you would say, I am here. I do know the gradient up to this point. Now, what is the gradient with respect to gamma? That's going to be the gradient up to this point times the gradient of y bar with respect to gamma, right? Or the gradient up to this point times gradient with respect to beta, right? Again, you can write down the chain rule, correct? And that's going to be like this. So you can simply compute the gradient with respect to gamma and beta. That's not a big deal. Basically, the gradient with respect to beta is what you have done in your assignment as well for B, the bias. That's the same thing. And this other guy is, again, same thing as we have done in chapter 2, I guess, right? Yes, we're chapter 3. Chapter 2, right. So that's the same thing. So you can simply do that, and once you have the gradient, you can update your weights, right? So the batch normalization weights can simply get updated in every mini batch, again, right? As before. That is no problem. Now, up to this point, we are all fine. So we got up to this point. This means that we have the gradient with respect to every single standard version, with respect to every single u, right? But now the thing is that I want to get back from gradient with respect to u to gradient with respect to y, right? And that is the big thing, right? That is the messy part. So how can I do that? Well, let's just focus on one particular u. So say this is one particular u. Say omega is 1, so it's u1, right? What is u1? u1 is the normalized version of y1, right? It means that you have y1 minus mu divided by sigma, right? So this guy depends on y1, obviously, because y1 shows up here, here, and here, and also y2, because y2 shows up in mu and sigma, y3, and so on, right? Now, the thing that you can say is that the R bar, or the sample loss you computed out of U, is going to also depend to everybody, right? And this dependency simply comes from U, right? Because from U on, everything is just going in parallel, right? It's only U to Y which is interconnected, right? So you could say that the loss that I'm going to get out of the first branch, the top branch of the first sample, is depending on everybody, right? Before the normalization. And that dependency comes from this messy part, right? Now, what I want to do, I want to just compute the gradient of a sample loss, say gradient of the first sample loss, r hat 1, with respect to any y. So you see that I put it y tau, right? So it means that I am computing the gradient of the sample loss, which I compute after this u1, right? With respect to y1, y2, till y omega, right? Everybody's cool, right? You see that. So now, how can I do this? Let me just do it once on the board for you, and then you get this equation. I want to compute the gradient of R1, R hat 1, with respect to some y, which is y tau, right? So omega here now is 1, okay? Omega is 1. I am just computing with respect to 1 tau. What I do know, that this r hat 1 depends on, I computed all the gradients up to u. So can you tell me, before looking at the equation, can you tell me how can I write that down? This is going, don't think about, think of y everything to be a scalar. You don't need to think about them to be vectors or tensors, nothing. No? Just do the chain rule. Don't care about that. U1 times y tau, right? Every single of them, right? I could again say that, well, this is a general lambda. This is a general lambda. I sum it up over all lambda, right? Lambda from 1 to omega. But do I need that? No, because I do know r hat 1 is only coming from u1. u2, u3, they do not participate in computing that, right? So I could just remove lambda, put it 1, put it also here 1, and then I just remove this summation here, right? You're clear, right? The only place where I have interconnection is u to y, and this is where it's going to show up, right? So this is what I mean by this equation. So if you want to write down the complete equation, you would say that, well, I need to know the gradient of the sample loss with respect to every u, and then I multiply it with the partial gradient of that u with respect to the corresponding y, but eventually I don't need to really think about all of it, right? So I only think about the partial derivative with respect to the corresponding u, because other u's are not participating in computation of that sample loss, right? And now here, again, you don't care anymore about the type of product. You're going to figure it out eventually, right? So I'm just putting that particular circle here. This means that there is one product here, right? But you don't care about that anymore, right? So if it's hard for you to follow, just think about you or everybody to be a scalar. Actually, in the next slide, I'm going to put it a scalar. Everybody's cool? OK, now, you have this one, and the only thing that is important now is how you can compute the gradient of u with respect to corresponding y, right? So you want to compute the gradient of u1 with respect to y1, y2 till y omega, right? And how you can do it, now, just to keep everything simple, just think about scalars, right? So one entry inside u. Just think about a scalar. Assume that u, everybody in this diagram, everybody is a scalar, is a number. It's not a vector, it's not a matrix, nothing, okay? Just a scalar, right? What you can say I want to compute the gradient of u, say for example u1, with respect to these guys, right? I start with y1, right? Or first of all, if I want to write it down, I'm going to write it down in this form. This is basically the gradient we had in the previous slide. I just wrote it down in form of derivative, right? The gradient of my loss with respect to any of these y's here, right, is going to be the gradient with respect to corresponding u times the gradient of u with respect to that particular y that I try to compute, right? Now, first thing, assume that tau and omega are the same. It means that I am talking about the loss of the first sample, and I want to know its derivative with respect to y1. So I need to get from u1 to y1, right? How can I write the chain rule? Can you tell me? Yes? u1 with respect to y1 directly, right? So if you look at this one, what is it? Derivative of u1 with respect to y1. What is it? 1 over sigma, and you assume that mu and sigma are constant, right? So this is going to be 1 over sigma. You see that, right? Am I over? No? I do have another thing. What is that? Derivative with respect to mu times derivative of mu with respect to y, right? So the next thing, so u1 with respect to y1, this is the first term, right? Second thing, u also depends on mu, right? So I should write it down, the gradient of u with respect to mu times derivative of mu with respect to y. Everybody's clear? You see that? You don't see it? So look at this guy. U depends on y, mu, and sigma, right? It's a nested function. Mu itself, sigma itself, they also depend on y and all other y's, right? So what you do, you would say, okay, how many partial derivatives you have for u? Tell me. You have a partial derivative directly with respect to y. You see it, right? Assuming y is your variable, don't think about the indices there. So y is just simply y, and mu is simply mu, sigma is sigma, right? If you are thinking about u1 and you are talking about y1, right? It's a direct function of y1, right? Because y1 shows up in the denominator, right? It is also a function of mu. It is also a function of sigma, right? So you have 3 partial derivatives, right? You see it? Yes, y2 appears here inside mu, right? Yes, but it depends how you define the variables, right? And right now, I am not thinking that way, so I see the confusion. So if you think about u1, right? Given the expression that u1 has, right, you just put omega to be 1. Let me write it here. So u1 is simply y1 minus mu, which is a function of y1 till y omega, right? Divided by sigma, which is again a function of y1 till y omega, right? What I'm going to do, I'm going to call it a function f, okay? And this function depends on, this is my choice, y1 mu and sigma, right? Okay? Now, what you want to know is what is the derivative of u1 with respect to y1 first, right? What you're going to say, you're going to say that, okay, I have derivative of y1, partial derivative of f with respect to y1, right? Times derivative of this guy with respect to y1, right? Partial derivative of y1 with respect to y1. What is this guy? 1. Plus. What is the next variable here? Mu. So partial derivative of f with respect to mu times partial derivative of mu with respect to y1. What is it? It's something, right? I'm going to compute it later. So next thing, partial derivative of f with respect to sigma times partial derivative of sigma with respect to y1, right? Everybody's clear? So you think like that, right? Now, if you wanted to compute this same thing with respect to y2 now, right? You want to know what is the derivative of u1 with respect to y2. You can do the same thing, right? You could say partial derivative of f with respect to y1 till partial derivative of y2 with respect to y1. What is that? 0, right? Great. Here, partial derivative of f with respect to mu times partial derivative of mu with respect to y2, right? Oh, sorry. Here should be y1. Sorry, I did a mistake here. And then partial derivative of f with respect to sigma times partial derivative of sigma with respect to y2, right? Now, if you want to just go ahead for any omega, then you would just put it omega. You would say for any omega, partial derivative of f with respect to y1, because y1 is the first variable here, right? Till times partial derivative of y1 with respect to y omega. Same thing here, same thing here. You see it now, right? Everybody's cool? Yeah. Yes, I mean index I inside U. So you just forget totally about U. So U is nothing. Like U itself is a vector or a tensor or something, right? It has I different entries. Yeah, but how about omega? Omega, no. Omega is like for the sample, right? So omega is the one which I'm writing on the board. So I am talking, when I say U omegas, if omega is 1, I'm talking about the first sample. If U is omega is 2, is the second sample, and so on. So what's I? I is entry I inside U omega. Because U omega is a vector, right? Also like U1, U2, there are vectors. Yeah, yes, of course. So they are vectors for different samples, right? Okay. You see? But I, you can simply forget about it right now. You can think of U to be simply a scalar. Then I does not exist. Okay? Everybody's clear? Yeah. Uh-huh. Yes. Yes. That's right. Okay, questions? So you got the idea, right? So once again, if I am talking about u omega and I'm computing the gradient of u omega with respect to y omega, the first guy is going to be the derivative of that f I wrote you on the board with respect to y omega times derivative of y omega with respect to y omega, which is 1, right? And what is the derivative of this f, this expression, with respect to y omega? What is it? 1 over sigma, because y is only showing up here. Mu and sigma are treated as constant because they are partial variables, right? Other variables. So this is going to be 1 over sigma, right? Plus, the next term is the derivative of that u with respect to mu, right? Times derivative of mu with respect to y, right? And the last guy is the derivative with respect to sigma times derivative of sigma with respect to y omega, right? Now, what is the derivative of u with respect to its mu? Minus 1 over sigma, right? Minus 1, because mu is just a variable now, right? So it's minus 1 over sigma. What is the derivative with respect to sigma? Is whatever you have in nominator times minus 1 over sigma squared, right? Because it's like some constant over sigma, you take the derivative, right? So this is going to be this one. 1 over sigma is going to stay here, so this one is going to be minus 1 over sigma. This guy, this derivative, is minus the same denominator as we have here divided by sigma squared, right? And then you multiply them with the derivative of mu and sigma with respect to y, right? Clear? Again, I do get it that you don't see the exact expression. I just hope that you'd see how we are doing the chain rule, right? That's the only thing you need to take. Okay? Now, if you keep on going, you can actually simply compute the derivative of mu with respect to y, right? If you are thinking about one particular y, mu is the average of those y's, right? What is the derivative of mu with respect to one particular y? What is it? 1 over omega. Great. So the derivative is simply 1 over omega. If you think in terms of sigma, what is it? It's going to be a bit more complicated, right? So you need to just expand the derivative, right? So you can keep on going like this. You can actually, again, use, chain rule, because this guy, this sigma, depends on y and mu, right? You can again write it in form of chain rule. Direct derivative with respect to y times corresponding one plus direct derivative with respect to mu times corresponding one, and so on. I don't want to bother you further with that, but if you do the calculation, you're going to end up with a compact expression, okay? So that one is just simple math. You can do it simply at home, okay? So the moral of the story is that these partial derivative, the partial derivative of mu with respect to y, the partial derivative of sigma, standard deviation with respect to y, are simple to be computed, okay? And you just take those guys, you replace them back inside the expression. This is the partial derivative of, okay, here is a mistake. So this tau, the first tau, it should be omega. Just fix it. So y, u with respect to the corresponding y, right? So what you see here is that this guy, this expression, the final expression that you have, is the derivative of 1u, say u1, with respect to its corresponding y, right? And this used to be super simple, right? Because before batch normalization, we didn't have any of this here, right? And this was a direct line. You can simply just move backward on that line, right? But now you have lots of lines, right? So you need to move backward on this line. Also, you need to get the other path. Also, you need to get the other path. And then this is going to conclude this expression. Okay? Now, what if I want to compute the derivative of u1, for example, with respect to another y? So not y1, but y2, say. Well, everything seems to be the same. There is only one tiny difference. And I think we did it on the board once. So say I do that. Well, I would say u1 with respect to y2, right? If I am taking the derivative of u1 with respect to y2, what's going to be the first term? 0, right? Because I am talking about u1, right? And I want to take the derivative with respect to y2. It's not directly connected to y2, right? So the first derivative is going to be 0. The remaining derivatives are going to be the same, right? And if you just do that, then you're going to end up with the same expression as before without the first one. Okay? And now, since you do know what is the derivative of every single u here with respect to all possible y's, you are over, right? So you do know how to move backward from u to y, and that's it, right? So you're going to just collect them here inside this mini batch average, and then you would say, if I want to compute the derivative of my r hat with respect to any of the y's that I have in my mini batch, then eventually I just need to do this calculation, right? So every single of those particular, cross derivatives, right? And you have all of them, right? So you can simply write this guy down in this form, but, well, this is just kind of compact form of what we did on the other slides. Derivative of the loss with respect to one particular y is whatever derivative you had before times this expression. And here is the indicator function, because this expression only shows up when your omega and tau, the index, is exactly the same. If they are not the same, then it's going to be 0. Rest of them are going to be the same, right? But again, I totally get it that this calculation is a bit messy. The key point here is that when you are going backward, you're going to trouble, right? And this is one of the first points in the course that you see it clearly, that knowing how the backpropagation works is very important. Because if you simply think of, oh, maybe I can take this entry, this neuron inside the neural network, and then do this on the samples and combine it with that one. Well, you can do it, definitely, right? But you should think about the backpropagation as well, right? Does it harm backpropagation? I mean, obviously, it's not harming here, because you can find it out, and this is not like a significant drop or any killing of gradients, right? But that could happen, right? So whatever is nice in the forward propagation should be also nice in backward propagation to work, right? And yeah, so you can simply compute the gradient with respect to weights in the same way as we have done before. I don't want to bother you with those details, because there is no point in just showing you more computations. But the key point is that we are just using chain rule, and we can always do backpropagation by doing the chain rule, okay? And if you would like, you can just go ahead, do it once again at home, do the complete one, to just see if you got every detail, okay? Questions? No question? So, moral of the story, batch normalization is going to make you stable, but you're going to do much more computation when you are backpropagating. That's one thing. Another thing that you might ask me is that, say I am finished with training, right? So when I am training, I learn to, for example, normalize every single hidden feature, right? And now the question is that if I want to use this for inference, like I put a new data, what should I use as the mean value and standard deviation to normalize that input and corresponding features, right? Because if I have a new sample, say a new image, it goes inside the neural network. In the first hidden layer, I'm going to get a bunch of features, right? When I used to do the training, I just wait for all of the batch, samples in the batch, right? And then I normalize with those samples, right? But I don't have any more samples. This is just this single guy, right? What should I use to just do the normalization, right? Do you see the question? Do you see the problem? You had a question, right?
Yeah, it was the previous slide.
Right.
Here's this gradient of the loss.
With respect to y.
Yeah, but shouldn't we multiply?
Oh, yes, because this is just a single neuron. I thought it's a single neuron. Yes, you're right. All of it should be multiplied with the gradient of the loss with respect to output. Sorry, that one is missed. Right. There's one gradient factor here missing.
On the line before as well, right?
Oh, no, here is okay. Gradient of the loss with respect to y is the gradient of the, this is one fine. I missed this gradient, right? This whole thing get multiplied with that gradient. That's right. Yeah, thanks. So, did you get the question here? What is the problem? So, if you are doing training, you have a mini batch, right? And all the mini batch comes in every layer. Then you have all those samples. You normalize, you go for the next layer, right? But if you are using it, like you're finished with training, you have a new image, you want to use it for inference, right? Then when you get into a hidden layer, you don't have any other sample to normalize with, right? The main idea is that we just use moving average of what we got during the training. So it means that every time in every single layer, you're getting one particular mu and sigma for every single mini batch that you sent, right? And every time you compute this, you just compute the moving average as well. So whatever you had before, you compute the moving average of that, guys, with this new one, right? And you keep this one going. When you are finished, then you use this one in order to normalize your new samples, right? Everybody's clear? So this is the typical one. This choice of alpha is obviously somewhere between 0 and 1 because it's moving average. But again, you can guess that we put it close to 1 because we want to rely more on the previous average rather than a new sample, right? No, you don't need to do that because these things are all happening entry-wise, right? So every entry is having its own mean and variance. So you don't really need to care about the dimension there, no. So one question here, and that question is that, okay, I forgot my question. I wanted to ask you a question, but I forgot that. So, well, sorry. So anyways, so yeah, so moral of the story, you just use the moving average when you are doing the training. You compute that, and then you use it for inference. That is going to help you. My question. Now, if you are implementing this in PyTorch, right, when you are doing the training, you use model.train, right? Is it crucial to just switch to model.eval when you go for inference? Yes, right? It's important. Again, like dropouts, right? Because in inference, you are using a different approach, right? You're using those moving averages, which you are not using in training, right? So again, when you are doing batch normalization, it's important that distinguish between training and evaluation, right? So yeah, that is the next point. And so finally, yeah, when you start with doing the moving average, so like any other moving average, you could start with just totally 0 for sigma, and this is a very unstable situation. So you usually start with some epsilon in the initial mini batches, and gradually when the mean just gets some non-zero value, then you can drop that epsilon, of course. And yeah, so doing the batch normalization, you can do it before activation or after activation. We did it here before activation. This was the classical form before, like in early days, but there is no reason that it's better to do it before activation, right? So you could actually do the normalization, like you get your SAM features, you activate them, then you do batch normalization, and nothing gonna happen, right? So it's exactly the same backpropagation as before. Now, in practice, you usually try both of them. If you see one of them is not giving you the robustness that you want, maybe you can try the other one. Maybe that one is doing better, right? So, and this is the last point that I wanted to make. So, train and eval is different here, right? So, like dropout, you should pay attention to that one as well when you're implementing. Any questions?